All right, today we're talking about waves. So Schrodinger, when we were talking back about the scientists who were discovering the atomic model, he was the guy who kind of came up with the idea that the electrons don't travel in these specific orbits around the nucleus like Niels Bohr thought they did. He said that they travel in wave patterns, and they are found in these clouds around the nucleus where there's different probabilities of where they could be. But his main thing was that they traveled in wave patterns. So in order for that to make sense, we kind of had to talk about exactly what waves are. So, what is a wave? In general, a wave is a disturbance that transfers energy. So, what does that mean? It means that if there is energy going through a substance and it's moving the particles as it goes through, then that is a wave. All right. Some waves require a medium to travel in, and a medium is just a substance that they're going through. It could be solid, liquid, or gas, and other waves do not require a medium. So the two different types of waves then are mechanical waves, which are ones that require a medium to move through. So like sound waves or water waves or waves in a spring system. Those are all mechanical waves. And you guys have probably heard the tagline from horror movies and stuff. It's like, in space, no one can hear you scream. That's because there's no air out there, so there's no medium for sound waves to travel through. Right? The other type of waves are electromagnetic waves, and those are the ones that do not require sorry about the dog. Those are the ones that do not require a medium. So anything on the electromagnetic spectrum, basically, which is all the way from radio waves, microwaves, visible light, what we can see, UV light, infrared light, and then up through X-rays and gamma waves and all that stuff. All of those are electromagnetic waves, which means they can travel through space or through a vacuum with no medium, no air or water or whatever to travel through. Okay, so here you can see the electromagnetic spectrum. This tiny little section of it here is what makes up all of the light that we see. You've got UV and IR on either side of that, and then as we go down into the larger wavelengths, so the waves are getting longer and longer there, you've got radio waves, and then off to the left in the higher wavelengths, smaller wavelengths, where there are little, very short spaces between the waves, we've got our X-rays and then our gamma rays. All right, so we're going to talk about all the different parts of a wave. So the first one is the crest. The crest is the very top, the peak or the highest point of a wave. All right, and all these say have a transverse wave, and all that means is that the wave motion, the up and down, is perpendicular to the direction the wave is traveling in. So this wave is traveling here from left to right, which means the motion of the wave is up and down. That makes it a transverse wave. All right, so here we've got a trough. So a trough is the bottom or the lowest point of a transverse wave. All right, wavelength is an important term to know, and that is the distance from the point on one part of your wave to the corresponding point on the next part. So here, from crest to crest, or peak to peak, the distance between those two would be one wavelength, or down on the bottom you can measure it trough to trough, that would be one wavelength, or you can even measure from like this equilibrium point here to this equilibrium point here, and that would be one wavelength as well. All right, frequency is the number of waves produced in a certain amount of time. So the more waves per second you have, the higher your frequency. The fewer waves per second, the lower your frequency. All right, and this also has to do with how much energy the wave can carry. If you have a very high frequency wave, it's going to have more energy in each individual particle of it, and the low frequency waves have less energy. And we'll talk more about that later at the end of the PowerPoint. All right, and then amplitude, so a wavelength is how far apart each wave is. Frequency is how many waves go by per second. Amplitude would be how tall the wave is, basically. So it's the distance from the resting position or equilibrium to the peak or to the trough, from the middle to one extreme. All right, so these ones here have a large amplitude. These ones over here are a small amplitude because there's not as much distance there. All right, and large amplitude waves, again, carry more energy. Small amplitude waves have less energy. All right, we've got to talk about velocity here before we get on to any of the calculations. So velocity is the speed that a wave travels through a certain medium. So like you guys have heard speed of sound. Well, sound actually travels at a different speed through different materials, but the speed of sound in air, what's most commonly referred to as the speed of sound, is 343 meters per second, or about 770 miles per hour. All right, so that would be the velocity of a sound wave. The speed of light in a vacuum, so how fast light travels through space, is 3 times 10 to the 8 meters per second, or 671 million miles per hour. So, very fast. Alright, so if we know velocity, and for like speed of sound problems, I will give you the velocity. For speed of light problems, velocity will be written as c, which is the constant for the speed of light, and it's always going to be equal to 3 times 10 to the 8th. So anytime we're talking about electromagnetic waves, unless I tell you otherwise in the problem, assume it's a 3 times 10 to the 8th for your velocity. Alright, so we can use the velocity as well as either the wavelength or the frequency to find the other one, depending on which one we know and which one we don't. And the equation that we're going to use to do that is this, where v is equal to, this symbol here is a Greek letter, it's called lambda. So we've got v equal to lambda times f. And lambda is the wavelength of the wave in meters. F is the frequency in hertz, or waves per second. All right, so here, if we're looking at some examples of that, move my mouse out of the way. This one here, it's talking about a sound wave, and so I've given you the velocity. I told you sound wave is traveling through the air at 343 meters per second and has a frequency of 500 hertz. What is its wavelength? So if we go in and look, we would have our equation written out as v equals lambda times f, and we can go in and start plugging stuff in. We know v, it's the velocity, it's told to us in the problem. So that's 343 meters per second. All right, and you guys don't have to write the units out, but I like to do it just to keep track. All right, and it has a frequency of 500 hertz, and we don't know the wavelength. The wavelength is what we're looking for. So the wavelength is going to stay as our lambda. And then our frequency we're going to plug in as 500 hertz. Okay, so if we're trying to solve this for lambda and find the wavelength, all we've got to do is divide both sides by 500 to get rid of it on that side. So this 500 divided by 500 cancels out. And we've got 343 divided by 500 is equal to lambda. And then we'll go ahead and go to our calculator and say 343 divided by 500 is equal to 0.686 meters. So that is lambda. All right, and your wavelength is always going to be in meters. Okay, so that was question 1. Question 2 is talking about a radio wave. So we talked earlier and we said that radio waves were electromagnetic waves. So that means its velocity is going to be this number here, c, the 3 times 10 to the 8th. So here we're going to set up the same thing. This time we've got c is equal to lambda times f, and c is 3 times 10 to the 8th. And this time it gives us the wavelength. So it gives us lambda, so we'll say that's 23. And it wants to know the frequency. So again, same thing here. All we've got to do to find frequency is divide both sides by 23. And that will tell us what our lambda is, or sorry, what our frequency is. So let me go back to my calculator real quick. And here I'm going to say 3 times 10 to the 8th power. Oops, that's not right. Divided by 23. And that's going to come out as 1.304348 blah 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 times 10 to the 7th. Okay, so this would be our answer for, my pen is running out of ink. This would be our answer for frequency, for F, in this second problem. Alright, so that is finding wavelength or frequency based on the other. The other thing we can do if we know wavelength or frequency is we can find how much energy is in a photon. Now this one only works for electromagnetic waves, so it's only going to matter for radio waves, light waves, gamma waves, anything like that. It won't be sound waves or ocean waves or anything like that. It's only going to be electromagnetic ones. Alright, and the equation for this is that energy is equal to h times frequency. Alright, h is a constant. It's Planck's constant. And this is the number for it. So this is always what you're going to plug in for h. And then you'll plug in frequency and use that to find how much energy is in one photon. So here we've got problem 1, which is how much energy is in one photon of a gamma wave that has a frequency of 9.8 times 10 to the 21 hertz. I should have put the unit in there. So here, if our equation is that energy is equal to h times frequency, we don't know E, that's what we're looking for, so we'll leave that as its variable. The Planck's constant, we can plug right in for h, 6.626 times 10 to the negative 34. That's right here. Planck's constant, always going to be the same thing. Alright, and then we've got times our frequency, which we do know, which is 9.8 times 10 to the 21st. Alright, so here, in order to find E, all we've got to do is actually multiply these two numbers together. And if you remember from when we were talking about scientific notation, the way to multiply scientific notation together is to take the 6.626 times the 9.8, our two base numbers, and multiply them together first. So let's do that. Let's say 6.626. Oh, I didn't quite get it. 626 times 9.8. That comes out as 64.9348. And it's going to be times 10 to the power of something. And the way we find that power is if we are multiplying these two numbers together, we have got to add our exponents. So we're going to add the negative 34 and the 21 together, and that will be the exponent in our answer. So we're going to say negative 34 plus 21, and that is equal to negative 13. So this would be our answer for how much energy is in one photon of that gamma wave. And this is in joules, by the way, which is abbreviated as J. All right, so the second one is a little bit trickier. It's got one extra step because it doesn't actually give you the frequency. Instead, it gives you wavelength. But luckily, because it's an electromagnetic wave, we can use that to find the frequency. So if you remember from the last set of problems we did, we know that C is equal to lambda times frequency. We know that C is always going to be equal to 3 times 10 to the 8th when we're talking about electromagnetic waves. And it gives us the wavelength. It gives us lambda. So we'll plug in here our 4.56 times 10 to the negative 6. And then times frequency. All right, so here, in order to find frequency, we've got to, here, let me scooch this up a bit so y'all can see. We've got to divide both sides by this 4.56 times 10 to the negative 6. So we're dividing both sides by the wavelength. All right, and that'll make it cancel out over here and give us just the frequency left. So just like the problem we did a second ago, when we are dividing scientific notation like this, the first thing we do is divide the base terms. So here we're going to say 3 divided by, 3 divided by 4.56. And that comes out as 0.658, we'll call it. We'll just round it off for now. And then for this one, when we are dividing our scientific notation, in order to find the exponent, you have to subtract these two. So here we're going to say 8 minus negative 6. And that should come out as 14. So our answer for this one, for the frequency, this isn't our overall answer, it's going to be 0.658 times 10 to the 14th power. Or if we wanted to rewrite it as correct scientific notation, we could say 6.58 times 10 to the 13th power. So that is our frequency. And then our second step will be to plug that into our energy equation. So we know that, here, I'm going to do it over here. We know that E is equal to H times frequency. So here we can plug in our H, which is the Planck's constant again. It never changes. Times 10 to the negative 34. That's not going to work. We're not going to have enough room. I'll just do it on the next page. So it's E is equal to Planck's constant, 6.626 times 10 to the negative 34, and then times our frequency, which was 6.58 times 10 to the 13th. And then we just multiply these together. The 6.626 gets multiplied first, times 6.58. This thing is not registering my clicks. There we go. So this is 43.6, we'll call it. And then it's times 10 to the, when we are multiplying, we add the exponents. So here we've got negative 34 plus 13 is equal to negative 21 as our exponent there. And then I guess if we wanted to make this correct scientific notation, we could write it as 4.36 times 10 to the negative 20, because now it has to go one less jump to the left if we move our decimal like that. Okay, so that is what we're working on today. You guys have got a homework with some problems like this to work through. If you've got any questions, just let me know.